Cohesionless granular soils, like dry sand or gravel, have no tensile strength. Without external support, they can only stand as steep as the angle of repose of the soil. At steeper angles, they slump. Many building and civil engineering projects require earthworks to be constructed at different levels across the site. To produce a level formation for a highway, for example, the land has to be cut on one side and filled on the other. Traditionally, engineers have two options. One is to create an unreinforced slope by battering back the soil to a slope angle at which it is stable. This option takes up large amounts of land and can cause slope damage. The other is to construct vertical cast-in-situ concrete walls to retain the unstable mass of soil. In this case, the land take is much less. Conventional retaining walls apply an external compressive restraint to control tensile strains developed in the soil mass. If this compressive restraint is removed, excessive tensile strains develop within the soil mass, which then starts to collapse until it reaches a stable slope angle. Both unreinforced slopes and retaining walls are acceptable engineering solutions. But there is a third option. This is to apply compressive strength internally by incorporating soil reinforcement. Many materials are used for soil reinforcement. These include high-strength fabric geotextiles in slopes or walls with wrapped faces, and polymer grids in modular block walls. After reinforcement is placed, initial tensile strains still develop within the soil. However, if the reinforcement is of low extensibility, these small strains lead to relative movement between soil and reinforcement. As these stresses are of opposite direction, they induce compressive stresses in the soil and complementary tensile loads in the soil reinforcement. The end result is a stable mass of reinforced soil comprising two zones. The active zone, in which the soil transfers tensile loads to the reinforcement, and the restraining zone, in which the reinforcement sheds tensile load into the soil. These processes of load transfer are the fundamental mechanisms of reinforced soil. The concept of internal load transfer is not new. This tower temple at Agar Guf was constructed in Mesopotamia around 2000 BC. The Tower of Babel was finished around 250 BC. Known as ziggurats, these structures look similar to the stepped pyramids of ancient Egypt. Typically, they were built of clay blocks reinforced at intervals with horizontal mats of woven reeds on a layer of sand or gravel. It was on a Mediterranean beach in the 1960s that French engineer Henri Vidal observed how pine needles seem to add strength to sand. His researches showed that friction developed between the sand and the pine needles transferred stresses from the weaker element to the stronger, creating a strong and stable cohesive material. With friction as the principle, Vidal developed the design concepts for what he called terre armée, or reinforced earth. His prototype reinforced soil wall was constructed in 1964, using steel strips to reinforce selected fill. 4 years later, this system was used to construct a major wall on the Autoroute de Menton in France. This particular system comprises 3 elements: selected fill, steel soil reinforcing strips, and semi-elliptical steel facing units. In the U.S., the first reinforced wall of this kind, 15 meters high, was constructed in 1972 on Route 39 in California. Since then, there has been an explosion of reinforced soil technology, new applications, design approaches, and construction systems. In parallel with steel systems, a whole new genre of polymeric materials is used for soil reinforcement. There are 2 distinct technologies for reinforcing soil: reinforced fill and reinforced ground. Reinforced fill is engineered fill incorporating discrete layers of soil reinforcement between successive layers of selected fill. By contrast, reinforced ground is natural ground or pre-existing fill reinforced by soil nails. The nails can be inserted by various techniques such as drilling and grouting, or by ballistic insertion, in which nails are fired into the ground. Reinforced fill comprises three main components: the facing, the soil reinforcement, and selected fill. Where facings are used, they may be classified as hard or soft, or facings may take the form of vegetative cover. Most hard facings are precast reinforced concrete panels or segmental blocks used primarily for the construction of vertical walls. Panels can be partial height or full height. Partial height panels come in many shapes: T-shaped, hexagonal, and many more. The so-called cruciform panel, nominally 1.5 meters square and weighing around 1 metric ton, is precast with steel lugs projecting from the rear. The panels connect together. Steel reinforcing strips are laid on top of the fill, and one end of each strip is bolted to a facing panel lug. In this similar system, steel loops protrude from the rear of T-shaped panels. First, a base course of facing panels is erected on a small concrete footing, which is cast in situ. Selected fill is placed in layers until it reaches the level of the first pair of precast loops. It is then compacted. Polymeric strip reinforcement is placed in a zigzag configuration and secured at the facing and at the inner limit of the reinforcement area. The reinforcement is then covered with a layer of compacted fill. Successive courses of panels, layers of reinforcing strips and fill are added until the required wall height is attained. In this case, the wall is finished with a parapet. Full-height panels are precast to suit contract-specific wall heights. Full-height panel walls are propped. Depending on the system being constructed, the prop may stay in position until the panel is backfilled and the soil reinforced to the required height. A variation is the king post and panel wall, often called the Spanish system. Full-height steel posts are erected in the form of universal steel column sections. These are faced with precast concrete planking slotted into the webs. For this bridge abutment, the soil is reinforced with geogrids. These are gripped between successive lifts of planking as the fill is placed. Finally, a detached brick wall provides a pleasing finish. Segmental blocks of various kinds can be used with strip reinforcement, but are most commonly used with geotextiles or geogrids, which are generally clamped between courses of blocks. In this system, polyethylene connectors join the facing to the reinforcing grid. To resist the shear that occurs between horizontal joints, blocks are usually manufactured with cast-in shear keys or shear clips, or to accommodate dowel bars. An extensive variety of modular systems is available. Once assembled, segmental blocks or concrete panels must be able to compress vertically en masse. Otherwise, differential settlement between fill and facing might shear the connection between facing and reinforcement. To overcome this potential problem, Vidal's elliptical facing units compressed vertically, like a concertina, in sympathy with the fill and embedded strips. For partial height panels, polymeric filler strips are placed on the horizontal joints of the facing panels. This allows several courses of facing panels to compress. Another alternative connection system allows the reinforcement to slide vertically relative to the facing panel. In Japan, a staged method of construction is often used to overcome differential settlement. Flexible, gravel-filled geosynthetic bags are placed at the shoulder of each soil layer, wrapped with a flexible geogrid, and secured with staples. Soil is placed up to the face, and compacted. After the settlement of the supporting ground and the fill, a full-height panel facing is cast in place. Soft facings can be wrapped or caged. Geotextiles and geogrids are soft facings. Being compressible and flexible, they serve to reduce shear loads in the fill reinforcement, which might otherwise be induced by differential settlement between facing and reinforcement. The simplest form of soft facing is wrapped facing, in which a geotextile or geogrid is wrapped around the face of the fill to form an envelope. Here we see a layer of geotextile spread out so that its free end extends over the face of the wall. A layer of fill is placed and compacted over the geotextile reinforcement up to the line of the face. The free length is then folded back to encapsulate the face of the layer of fill. As this process is repeated, each layer of fill bears on the previous layer of reinforcement, so preventing the wrapped face from pulling out. The use of hybrid climbing formwork for wrapped faces allows the fill at the face to be compacted to an acceptable level. It also enables construction to high standards of alignment and appearance. Caged facings are formed as discrete units rather than as an extension of the main fill reinforcement. Examples include geomesh gabions, geobags, filled steel box cages, or geocells. In each case, the fill reinforcement is either attached to or entrapped between the facing units, which are progressively stepped. Here, a combination of gabions and geogrids is used for this newly constructed slope. The reinforcement greens over gradually as pre-seeded plants become firmly established. This type of steel grid facing is a slightly different version of the caged facing. With an inclined arm bent to a predetermined angle, a planar slope can be constructed. The grids also provide formwork that allows the fill to be compacted right up to the required line. These cages stabilize the face over the design life of the slope or wall, especially against the effects of erosion. The steel grid may also be used purely as a construction expedient that is allowed to corrode within the design life. As plants and bushes take hold, their roots contribute to long-term slope stability. As a generalization, hard facings are used in the construction of vertical walls or very steep slopes, while wrapped facings are used mostly for slopes with angles between 45 and 70 degrees. Caged facings are typically inclined at 60 degrees to the horizontal. Flatter slopes may not warrant a facing, but are vegetated to protect against erosion. Facings take different forms, but all facing systems must enable construction within the specified tolerances, perform within these tolerances over the specified design life, sustain prevailing differential settlements without structural damage to the facing. Connections between the facing and reinforcement must also be able to sustain any differential settlement between the facing and fill. Vegetative cover is used for both steep and gentler slopes. Strong geotextiles and basal mattresses may be used to reinforce the base of embankments constructed over weak foundation soil, but in two different ways. A layer or layers of a high-strength geotextile can be placed across the base of an embankment constructed rapidly over a deep deposit of soft clay. The fabric provides stability to the embankment during the short term and becomes redundant once the clay foundation soil has consolidated and gained strength. Where the depth of the soft clay foundation soil is limited and there is a competent stratum below this, reinforcement may be obtained by installing a basal mattress. This consists of a series of interconnected geogrid cells constructed on the surface of the foundation soil. Filled with selected granular material, the cells form a foundation raft for the embankment. Neither a geotextile nor mattress basal reinforcement will reduce the amount of foundation settlement. However, the basal mattress can reduce the degree of differential settlement between the toe and center line of the embankment. Settlement may be reduced even further by constructing the embankment on piles used in combination with basal reinforcement. Without reinforcement, sudden and dramatic settlement may result from collapse of subterranean voids, such as mine workings or limestone caverns. In such cases, strong geosynthetics previously placed over the void may limit subsequent deflections. From facings, we now turn to the second component of reinforced fill, the soil reinforcement materials. Soil reinforcement can be metallic or polymeric. Both materials serve the same function, but each behaves in a different way. Metal reinforcement is in the form of carbon steel rods, strips, and grids, usually galvanized for protection against corrosion. Most metal reinforcement comes in plain or ribbed steel strips. Ribbing increases surface roughness to resist pull-out of the strip from the fill. Polymeric reinforcements are formed from polymer compounds that contain various additives. The polymers most commonly used for fill reinforcement are polyester, polyethylene, and polypropylene. High-strength aramids and glass-reinforced plastic strips, GRP, have also been used. The basic element in high-strength polyester soil reinforcement is a fine, continuously extruded filament, typically 30 microns in diameter. In this form, small quantities of these filaments are used for construction of randomly reinforced fill, where filaments and fill are applied together. However, most polyester reinforcement goes through further stages of production. These reinforcing strips we saw earlier are made of polyester filaments sheathed in polyethylene. Polymeric strips can be mounted in parallel arrays on a non-woven geotextile substrate to form a unidirectional reinforcement. These geogrids are used for reinforcing an embankment constructed over piles. Alternatively, these strips may be arranged orthogonally with thermally bonded junctions to form heavyweight bidirectional geogrids. Finer polyester geogrids are produced by forming a skeleton of orthogonal arrays of multifilaments or low-twist yarn with knitted or interwoven junctions. These grids have a protective coating of PVC, polyolefin, or other materials, and are suitable for the construction of vertical walls or steep slopes. Polyester multifilaments may also be converted into a low-twist yarn, which is then woven conventionally to form a high-strength geotextile sheet. This type of fabric is employed for the basal reinforcement of an embankment constructed over soft ground. High or medium density polyethylene is used to produce punched and drawn geogrids. Drawing or stretching the polymer causes the molecular chains to orient in the direction of drawing. This molecular orientation increases the tensile strength and deformation modulus of the polymer. Consequently, most geogrids are drawn in one direction and are said to be uniaxially oriented. These are suitable for reinforcing walls or slopes where the principal reinforcement is required in a direction normal to the line of the face. Biaxial polyethylene geogrids are formed by heating and stretching in two directions. These are used where axisymmetric loading may occur, such as in the reinforcement of roads. Polypropylene is the most commonly used polymer in the production of geotextiles, but is rarely applied in long-term soil reinforcement because it tends to creep. However, polypropylene biaxially oriented geogrids may be incorporated as a secondary reinforcement in slopes or in road reinforcement. Polypropylene is also used in the manufacture of heavyweight woven tape yarn geotextiles. So far, we have considered the first two components of reinforced fill, facings and soil reinforcement. The third is a selected fill. Reinforcement, polymeric or metallic, is buried in selected fill. For walls or steep slopes, a higher quality fill will be used in the reinforced zone than in the restrained reinforced mass. The angle of the slope of a pile of soil, measured from the horizontal, is closely related to phi dashed, the effective stress internal angle of shearing resistance. This is the basic parameter defining the shear strength of dry, cohesionless granular soils. The value of phi dashed will vary according to the particle sizes and density of the soil, but will typically be between 30 and 50 degrees. Clayey soils may have a phi value of less than 30 degrees. The ultimate unit shear stress that can be developed between the fill and the reinforcement is related to the phi value of the fill and the surface roughness of the reinforcement material. Simply put, the better the grade of fill and the rougher the reinforcement, the higher will be the unit shear stress generated between reinforcement and fill. The phi value will also influence the loads imposed on the facing units and the tensile loads transmitted between fill and reinforcement. These loads will increase as the phi value decreases. These interrelationships heavily influence design and also construction, where it is essential that the specified tolerances be closely applied. For example, if the facing is a precast concrete partial height panel, a high grade of fill is needed to achieve the specified tight construction tolerances. A fine-grained soil with a significant clay content would tend to squeeze laterally and press against the facing. On the other hand, a slope with a wrapped face, with more relaxed construction tolerances, may allow adequate compaction of a lower grade of fill. During construction, equipment should be kept off the reinforcement, and fill should be placed carefully to avoid damaging it. Once construction is complete, the fill must remain stable over the specified service life. The fill must therefore not suffer significant creep or compaction under its own weight, nor be prone to collapse, swelling, shrinking, or internal erosion if it becomes wet. It is important that any chemical elements in the fill do not cause the reinforcement to degrade beyond design limits. Combinations of facing, reinforcement, and fill are dictated by the end use of the reinforced soil facility and the design. However, certain combinations emerge. For example, steel strip reinforcement tends to be used with partial height facing panels and non-corrosive, well-graded granular fill. Geogrids may be used with more finely graded soil because their large embedded area allows them to develop high pull-out resistance. Geogrids are often used on steep slopes constructed with segmental block facings or caged soft facings. Polymeric reinforcements have greater resistance to chemical attack and may therefore be combined with more chemically aggressive fills, including industrial wastes. However, care should be taken when placing polyethylene in highly oxidizing environments or polyester materials in highly alkaline environments where there is also considerable heat or moisture. We have seen how the facing, reinforcement, and fill interact to form a reinforced soil system, reinforced fill. The next section presents the principal design concerns for reinforced fill structures. Design should provide against all conceivable failure mechanisms that might occur within the specified design life of the reinforced soil facility. Clearly, if the facility were to collapse outright, this would constitute a failure defined as an ultimate limit state of collapse. However, if the facility suffers unacceptably high deformations, which interfere with the intended end use, this failure would be regarded as a serviceability limit state. Design concerns include walls and steep slopes, basal reinforced embankments, and design life. For walls and steep slopes, failure mechanisms that might lead to an ultimate limit state relate to internal stability and external stability. Within the reinforced mass of a wall or steep slope, a potentially critical failure surface may divide it into two zones, the active and the restraining zone. The self-weight of the fill within the active zone, plus any other applied loading, may exert lateral earth pressures on the facing, which in turn induce tensile load in the soil reinforcement. If the tensile load applied to the reinforcement exceeds its strength, the reinforcement will rupture. But if the reinforcement is strong enough to resist the load imposed on it in the active zone, this load will be transmitted along the reinforcement towards the restraining zone. If the length of reinforcement in the restraining zone is too short, it will pull out, causing bond failure. In walls and slopes, the length of the reinforcement, L sub B, must be sufficient to bind the active and restraining zones together. To avoid deformations that could cause a serviceability failure, the tensile strain developed in each reinforcement must be less than the specified value. With internal stability assured, the reinforced mass is assumed to act as a monolith. The designer must then consider external failure mechanisms. Ultimate limit states include bearing and tilt failure, forward sliding, and overall stability. In considering serviceability limits, the designer will assess the total and differential settlement that can be tolerated. Design of basal reinforced embankments is carried out in two separate stages. Stage 1 is to make a long-term analysis using drained soil shear strength parameters. The assumption is that the soft foundation soil has been completely consolidated under the imposed embankment loading. The stable long-term embankment geometry is also determined, such as the inclination of side slopes, crest width, and embankment height. Stage 2 is to reanalyze the long-term embankment geometry using the short-term undrained shear strength for the foundation soil. This time, the foundation soil is assumed to be in a weak, unconsolidated state and not strong enough to support the embankment. A sufficiently strong basal reinforcement is therefore used to raise short-term factors of safety to acceptable levels. The next objective is to consider the four main mechanisms leading to ultimate limit states of failure. First is the rotational stability along circular failure surfaces passing through the embankment and foundation soil. It is assumed that a basal layer of reinforcement will provide the required tensile strength and also have sufficient embedment to ensure that it will not pull out from either the active or restraining zone. Similar considerations apply to failure mechanisms causing lateral sliding of the embankment fill or lateral extrusion of the soft foundation soil. Finally, the overall stability of the embankment is checked to guard against failure involving a deep-seated slip surface. It then remains to assess failure mechanisms leading to serviceability limit states. These include limitations placed on tensile strains developed in the basal reinforcement and settlement of the foundation soil. Design lives may range from a few months for a temporary facility to 120 years for a permanent structure such as a bridge abutment. Design life is largely controlled by the ability of the soil reinforcement to provide the requisite stabilizing forces over the required service life. With appropriate design, reinforced fill is highly resistant to seismic loading. The agent of degradation for steel is mainly electrochemical corrosion, while for polymeric reinforcement, it is primarily creep. The load that a reinforcement could sustain will therefore decrease with increasing time. This fact will be allowed for in design. In the case of reinforced fill walls and slopes, the tensile force, T sub R, required to maintain stability over the design life remains sensibly constant. In contrast, the ultimate tensile restoring force, T sub A, provided by the reinforcement, will decrease over time due to corrosion or creep. The reinforcement must therefore provide a restoring force with an adequate margin of safety against tensile rupture to meet serviceability limits. A different case applies to basal reinforced embankments. The restoring force required to maintain stability, T sub R, decreases over time as the foundation soil consolidates and takes an increasing share of the embankment loading. However, due to the effects of creep, the restoring force made available by the reinforcement, T sub A, also decreases over time. So, if a low creep reinforcement is used, the need for it decreases as the foundation soil consolidates. Since Vidal's work in the 1960s, soil structures reinforced with steel and a host of geosynthetic materials have become part of the daily scene. With so much achieved so far, the opportunities seem limitless for the 21st century.